Hi, RDBury here. This time I'm going to do something a little bit different. We're going to play with a calculator for a bit, and then I'm going to switch over to a spreadsheet. Um, First of all, I'm calling this video a system of arithmetic invented by a kid. And first, let me remove the suspense by justifying that statement. Was invented by George Bergman in 1957, and he was born in 1944. Is that right? Hang on. 1943, yeah. So he was born in 1943, so he was at most 15 when he invented this thing, maybe 14, but definitely in my book a kid. Um, I'm going to start on this, first of all, with the calculator. Basically just kind of playing around with it, seeing how this might come up naturally if you're just doing this, just kind of play on the calculator. Um, it it he George Bergman did not have calculators like this in 1957, but he must have been doing a lot of like hand calculations and stuff like that. I'm not sure, but anyway, however he came up with it. Nowadays, with the current technology, it's something you might stumble across. Anyway, so let's do a quick review. What is a base, number base? Well, we normally work on base 10. Let me switch over to scientific. What I'm going to do is put pi in there and store it in memory, and go over back to standard. So just so we have a something to work with here. So there's pi. What we have here is a string of digits. Basically, a base. What a base does is it turns each number into a string of digits. Now, this is base 10, but there are other possible bases. And let's look at, say, base 3. Now, what you do is you divide the number by the base until you get a number between 1 and 1 and whatever the base is. So in this case, if my base is 3, I need to divide by 3 once at least. So divide by 3. Now I've got a number between 1 and 3, so my first digit is 1. And to proceed, I just subtract whatever that digit is, whatever's left of the whatever's the integer part of that, or the whatever's left of the decimal point, and then multiply by the base again. So I subtract 1. I get 1, multiply by 3. That's a 0. So the first two digits are 1, 0. And now I've back to the original scale. So that's where I put the decimal point. So it's 1, 0 point. Multiply by 3 again. I get another 0 times 3. That's a 1. So far it's 1, 0.01. Multiply by 3 again. That's a 0. And now a 2. So 1, 0.0102. And just continue on in that fashion. Now there's a 1. subtract 1, another 1, and continue on like that. Now in base 3, the only possible digits you can get are 0, 1, and 2. With base 10, the only possible digits are 0 through 9. With other bases, with a base, you get from 0 from any digit from 0 up to but not including the actual base itself. So you could do that with base 2, and there's special names for these. There's binary for base 2, ternary for base 3. Other bases have other names. Decimal is base 10. It was kind of it was kind of wondering. People were kind of wondering for a while whether base 10 is actually the most efficient possible base. It isn't, but it's the kind of thing where it's so entrenched now that no one's gonna change it. I mean, it's basically it would be so much trouble to change it, even to something that was much more efficient, and the differences are not that big, but it would be more trouble to change than it's worth. So we're gonna pretty much have base 10 unless we totally destroy civilization and have to re-evolve from cave people again. So let's go back to our number pi here. So let's clear that. Now, so far I've said, well, there's base 2, base 3, base 4, etc. The one requirement that we need is that the number has to be greater than 0 or greater than 1. If we try to use base 1, we just when we do that initial division, we'll never get a number between 1 and 1. So we need a number greater than 1. But what happens if we don't assume that it's going to be a whole number? I mean, could we have a base 1.5 or base 2.5 or base pi or base some other number, base square root of 2, something like that? And it turns out the scheme does work. The thing is that it isn't always very interesting. In fact, it rarely is very interesting. If I do like a number like square root of 2, you get this string of digits here. After the first few, you don't really care what the rest of them are because they're just sort of random. And that's the kind of thing that happens a lot with these odd bases. So let me just show you how that might work. Let's do pi-based 2.5. So I divide by 2.5. Subtract. That's the number between 1 and 2.5. So I subtract the 1. Now I multiply by 2.5. Now I have a 0. And now I have a 1. So far I have 0.1, and then it continues on something like what happened with the base 3. But one thing you might want to have with a whole number as a base is that the whole numbers would at least have some kind of pattern to them, or maybe even stop eventually. So let's try a couple of numbers that might, and see if there's any kind of simplicity that might show up. So I'm going to start with, let's say, 3 base 2.5. So let's start with 3 divided by 2.5. First digit is 1 times 2.5. Next digit is 0 times 2.5. Next digit is 1. And let's just continue this. I won't narrate anymore. So you get this kind of sequence, but it doesn't get any more interesting here. It just gives you kind of this random like sequence of digits, and there's no real pattern here. I mean, the numbers always have to be between 0 and 2.5, which is, since they're all going to be whole numbers, it just means between 0 and 2. You're going to get zeros. The 2 is going to be kind of rare. I don't know if I can get one here, but it is possible to get the 2. But other than that, there's no real pattern to it. You can say something about the probability of a 2 versus a 1 and a 0, but other than that, it's just random. So it's not, to me, it's not that interesting. And you can try different numbers. Let's try square root of 2. Now you might think that square root of 2, since the square of 2 is 2, you just take the expansion base 2 and put zeros in every other place. And that seems probable, but it's not actually the case. And what I'm going to do is do 3 base square root of 2. So let's put square root of 2 in our memory here, so we don't have to keep typing it in there. Now I'll do 3 divided by square root of 2, and you see I can divide it 3 times before I get a number between 0 and the base. So that's the point here. You might think, well, 2 base square root of 2 is 100, and 1 base square root of 2 is 1. So 3 base square root of 2 must be 101. But that doesn't actually work, because when you expand it out, you get a number that is greater than the square root of 2 cubed. So the actual expansion must start with 4 digits before the decimal point. It looks like it's going to be 1,000 something. And if I continue, let's see if I actually do that. See, so I'm going to multiply by the base here. So there's 1, 2, 3. That's my 1,000, and then I have a point, and then 0, 0, 0, 0, 0, 0, 1. I might have one more 0 that I needed in there, but and this number doesn't look anything like what I started with. So if I subtract the 1 again, multiply by my base again, multiply by base, I get lots of zeros, but there doesn't seem to be any rhyme or reason to when the 1s appear. And again, they're just sort of a random, other than the fact that the 1s appear very rarely in this case, there isn't really much in of a pattern there. So base square root of 2 turns out, even though you might think that you just modify base 2 slightly, it doesn't really work that way. And you can try other, famous numbers. There's, you could try pi or e or whatever. Cube root of 2. But one famous number is phi. It's so-called golden ratio. So let's try that one. This is the kind of thing, if you've been exposed to math on YouTube, you've probably heard of the golden ratio. So what I'm going to do is first of all compute the golden ratio. It's 5 square root of 5 plus 1 divided by 2. Store that in memory now. And let's do 2 base phi. So 2, I need to divide it until it's between 1 and the base. So divided by phi, that's 1. Subtract the 1. Now multiply by our base. So now I get a 0. The first two digits are 1, 0. And now a 0. And now I just get 1. So this expansion actually just stops. 2 base phi is actually 10.01. So I'm going to switch over to the spreadsheet now and do some set up the spreadsheet so that it can compute this stuff without doing as much work. And I will see you there in a second or two. All right, well, now I'm in LibreOffice. I've started a new sheet here. LibreOffice is kind of a office-like an office suite in freely available. And I'm just going to start filling in the stuff that we've been doing in the calculator so far. So let's start out with our base, and I'll label that. And let's start out with base 10 to start to just to make sure things work properly. And our number, and let's use pi as our example. Right. Okay. So there's our number pi. We also need an offset to allow for the number of times we had to divide by the base in order to get our starting number. So in this case, I'm going to start with 0. And I'm going to do my calculations over here. So the first part is I'm going to take my number and then divide by the base the number of times is shown there. So that's going to be divided by, and then the base to the power of this number there. So that basically didn't do anything. If I change this offset, it would account for the division by the base, though. And then to get this number, so over here I'm going to put the actual digit, and the digit is just the part to the left of the decimal point. So I'm just going to say int of this. And I'm just going to allow, there's some potential problems with rounding error here, because you're cutting off at 0, so that if you get a number like 0.001, 999999997, and that's basically 1 with rounding error. So to allow for that, I'm just going to put in a very small adjustment there. So plus, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, and then a 1. So that should account for rounding errors without actually changing this number here. So so that's the first digit. Now to get the next digit, I subtract the digit from the number here. So that's this minus this. And then I multiply by the base, so times that 10 there. And that will give me the starting the second digit. Now I'm going to put the dollar signs in there. Oops. Dollar signs. There we go. And well, that will do is it'll make sure that that cell stays put when I copy this formula around. Because I always want to divide by the base, not by something else, or multiply by the base. This number I could just copy, or the formula I can copy, and that gives me the 1. And now to get the rest of the digits, I just expand this down. So that gives me the 3.14159265535, and whoops, I am going to delete the rest of them there because they're probably not accurate. See, you get rounding error there, and after a certain amount, you're just basically each time you expand the rounding error by a factor of 10, so eventually you don't have anything but rounding error. So anyway, that seems to work for base 10. Let's try base 3 here. And I need to increase my offset by 1 because this number is now between 0 and the base. So let's increase that. So now I've got 10.01021101. That's what we had before, I believe. So that's the expansion of phi-base 3. Let's try base. Let's try 3 base 2.5. It starts out 1 0 1 0 1 1 1. Let's see if I can get any 2s in here. There's a 2. So 2s are very rare in this base, but they do exist. And you also notice here that there's no real pattern to the digits here. I mean, other than the 2s being rare, there's still just sort of random numbers or random digits. Let's try let's try 3 base square root of 2. So I'll put square root of 2 in for my base. I need to increase my offset because this number is not is still bigger than my base. I'll increase it to 2. And it's still bigger than square root of 2, so I need to increase it again. So now it's in the right range there, and I get this. So the expansion is 1, 0, 0, 0 point, and then all these zeros, and then another 1, 0, 0, 1, and then more zeros. And now ones are fairly uncommon, but other than that, doesn't seem to be a pattern to where they occur. So again, square root of 2 does not really, I mean, you do get an expansion, but it doesn't really give you like an interesting pattern there. And now let's go to phi. So that's 1 plus the square root of 5 divided by 2. Right, I'm missing a parenthesis in there. Okay, that's correct. And let's do 2 to start out with. I don't need, let's see, I just need an offset of 1, I think. So that's between 1 and phi. And I get that 1, 0.01, and then it just stops. See, I get just zeros from then on. Let's try 3 now. And I need to increase my offset now. So that's in the hundreds range. So it's 100.01. And again, it stops. Let's try 4. And this kind of makes sense because if I add 1 to the 100.01, I get 101.01. So there does seem to be something of a pattern there. If you remember with square root of 2, that didn't necessarily work, and there's rules for how you need to deal with that, which I'll cover next time. Let's try 6 now. So this is too big, so let's increase our offset. That's in the right range. So our expansion is 1010.0001. So you can see as you get your numbers get bigger, then the length after the decimal point gets, or the expansion gets longer and longer and continues farther and further off or away from the decimal point, but it does always seem to still stop. And so that makes phi kind of special in that respect. And this is one reason that this is actually an interesting form of arithmetic here, because there are some interesting patterns you can get. It's not just random noise like you get with some of the other bases. So anyway, I guess I want to wrap it up there. But one point I want to make before signing off is that this kind of shows that you can, even as an amateur, you can make some interesting discoveries in math. Now, this George Bergman was kind of a one in a million shot because it doesn't really happen very often. I mean, there are a lot of people who have worked on math for a very long time, very smart people. Almost everything you're going to think of has already been thought of before. So don't be too disappointed that if what you've discovered is already been discovered. But once in a while, if you're very lucky and really think outside the box, so to speak, you might find that you find something that no one else has discovered before. And another thing it shows, at least to me, is that in math, the Mathematics magazine where this was published, they didn't say, okay, where did you get your degree from? We're not going to publish anything you say unless you've got a PhD. They just looked at the actual math. They said, well, it's correct. It's interesting. Our readers might be interested. Um, let's go ahead and publish it, even though it's basically from a kid. So I think that's a really interesting thing about math is that you get that kind of egalitarianism going on there. Anyway, I'm going to wrap it up there. Hopefully, I will see you next time when I actually go into some of the rules of arithmetic for this base. That's covered in the original paper to a large extent. But I'm just going to do it in YouTube format. And until then, I'll just say goodbye. Bye.